Chapter 1.5 is differentiability and continuity. So let's start with differentiability. So in the previous section, we defined differentiability of a function at x equals a in terms of a limit. We had the limit definition of the derivative. And if the limit does not exist, we say that the function is non-differentiable at that point, x equals a. And geometrically speaking, or graphically speaking, there's a couple different reasons why a function may not be differentiable, meaning we cannot take the derivative at a certain point. So here are some examples of non-differentiable points at x equals a. The first one is the graph could have a cusp. So a cusp is a sharp point or a sharp turn on a graph. What that means is that it has no tangent line at that point. So you can see in these first two examples right here for the first one, for top left graph, there is a cusp at that point, a sharp turn. There's no tangent line there. The graph has no slope at that curve. Next one, one on the right, top right graph, once again, we have a cusp. It is a sharp point. There's no tangent line there, meaning it is non-differentiable at x equals a. The next one is that the graph could have a tangent line that is a vertical line. And we know that that's going to be non-differentiable because vertical lines have undefined slopes. So in these two last examples down here, well, actually, this one on the left, the bottom left, that looks like a cusp also. It's a sharp point. But the one on the bottom right, the graph would have a vertical line at x equals a for a tangent line. So you can see that if you draw the tangent line, it looks like it's going to end up being a vertical line. There's no cusp there, but if you draw that tangent line, it looks vertical, meaning it's non-differentiable at that point. Okay, so those are the two examples of functions or graphs that would be non-differentiable at a point. Now for continuity. Continuity and differentiability are pretty similar, which we'll see how they're related in a second. So we say that a function is continuous at a point x equals a if it has no breaks, that should say breaks, not beaks, no breaks, jumps, or gaps as it passes through the point. So what this kind of just means in the most simplest version is we can draw the curve without picking up our pencil at all. That would mean that your function is continuous. So the actual definition here is as follows. A function f of x is continuous at x equals a, provided the limit of f of x as x approaches a equals f of a. So that means the limit is going to one place and the function evaluated at that point is the same exact value as the limit. So technically for this to hold, these three cases must be satisfied. First one, the function has to be defined at x equals a, so f of a has to actually equal a value. Second one, the limit of f of x as x approaches a has to exist. And the third thing is that those two, 1 and 2, have to be equal. The limit of f of x as x approaches a has to equal the value of f of a. And then if this is not continuous at x equals a, we say that it is discontinuous at that point. Okay, let's see some examples. We want to determine whether these functions are continuous at x equals 3 using that limit definition. So the first one for a here, top left, we have this curve. Here is x equals 3. So if we find the curve at x equals 3, we can see there is a hole, which probably seems pretty obvious that it's not continuous because we can't draw it without picking up our pencil. But using the limit definition here, we would say the limit as x approaches 3 of f of x does not equal f of 3. So the limit as x approaches 3 seems to be 2. And then f of 3 is obviously 4. It's actually written out there for us. So these are not the same, so that means it is not continuous at x equals 3. Let's take a look at the next one. So let's look at B in the top right here. So B, looking at x equals 3, here's 3 and we go up. Once again, hopefully it's pretty obvious that it's discontinuous because there is a jump. We're not going to be able to draw it without picking up our pencil. But using the limit definition, we would say the limit of f of x as x approaches 3 does not equal f of 3, because the limit actually does not exist, because the limit from the left does not equal the limit from the right, so the limit doesn't exist. And f of 3 is where the closed circle is, the filled in circle, which is right up here, which looks like it's about 2. So since one of them doesn't exist or is undefined, automatically it's not continuous, and obviously they're not equal, so once again it's discontinuous at x equals 3. And taking a look at these bottom ones, so for C on the bottom left, and taking a look at x equals 3, we have this vertical asymptote here. Once again, obvious that it's not continuous, that it's discontinuous at this point, because these curves are never going to meet because of that vertical asymptote, which means the limit of f of x as x approaches 3 does not equal f of 3. The limit here, the limit would actually be infinity. Or sometimes we say does not exist, but it's good to say infinity actually, because they're both going to infinity from both sides. And then f of 3 does not exist here, so we would say undefined. So typically for limits, if they don't exist, you say does not exist. For a function evaluated at a number, we say undefined. Hey, so since one of them doesn't exist, one of them is undefined, automatically this is discontinuous at x equals 3. And then the last one over here, on the right for D, taking a look at this at x equals 3, so clearly we have a hole here. So this is going to be discontinuous, and once again we say the limit as x approaches 3 of f of x does not equal f of 3. The limit, it looks like it's approaching a y value of 2, so that would be the limit. And f of 3 here, there's no filled in circle at x equals 3, so this is undefined, similar to one that we already did. So since those two are not equal to each other, it's discontinuous at x equals 3. So that's pretty much it for continuity and when a function is discontinuous. Hopefully pretty simple for that one. And now for the last thing, let's check the relationship between differentiability and continuity. So the relationship between being able to take a derivative and whether or not a function is continuous. So here's the relationship between them. If f of x is differentiable at x equals a, then f of x is automatically continuous at x equals a also. So notice that the reverse statement is not true. We can't say that if a function is continuous, then it's automatically differentiable. So taking a look at this example right here, down here at the bottom with this graph, so this function is continuous because we can clearly draw this without picking up our pencil. We can trace it like this, so it's continuous. Clearly the limit as x approaches a is going to equal f of a, because they're both going to equal whatever this y value happens to be. But we know that it's discontinuous. We know that it's discontinuous at x equals a because there is a cusp. Okay, so differentiability implies continuity, but the reverse statement is not necessarily true. Okay, so that is actually it for this section. That's differentiability and continuity and how they are related to each other.